Hello and welcome to our lesson on solving systems of linear equations in two variables. This is going to cover three sections from our text, section 3.1, 3.2, and 3.3. We've got a lot of ground to cover, so let's get started. I guess the thing I want you to know right off the bat is when you're solving a system of linear equations, what you're actually looking for is the point of intersection. So if you think about lines, normally if you graph more than one line in the coordinate plane, those lines are going to cross. And the point that they cross at is the solution of the system. So just keep in mind that we are looking for the point of intersection of two lines in these sections. Now we are going to cover four techniques for solving a system of linear equations. And the order we're going to cover them in is graphing, then we'll look at substitution, then the addition method, which is also known as the elimination method, and last we're going to look at how to use my calculator, the Casio FX991EX CLASSWIZ, to solve a system for us. For our first example, we're going to look at problem number 1 from section 3.1. The instructions say solve the system by graphing. Since these equations are in standard form, that means we're going to use the Intercepts method of graphing. And I'm going to try to color code this. So the first equation in blue, if I use the Intercepts method, that means I'm going to let x be 0 one time, and then I'm going to let y be 0 one time. So if I let x be 0, that's going to give us 0 plus y equals 4. 0 plus y is just y. And so that gives us an ordered pair of 0, 4. Then if I let y be 0, that's going to give us x plus 0 equals 4. X plus 0 is x. And so that gives us the x-intercept. Next, I want to go to the coordinate system. I want to plot those points. Notice that those are on the axis. That's why it's called the Intercepts method. And then if I connect the dots, I get a line through like that. Okay, next, the second equation in green, again using the Intercepts method, if I let x be 0, that's going to give me 0 minus y equals 2. 0 minus y is minus y equals 2. And then if I change the sign on both sides, that's going to tell me y is negative 2. Then if I let y be 0, that's going to give me x minus 0 equals 2. X minus 0 is x, and there's my x-intercept. Then we're going to go to the coordinate system, 0, negative 2, and 2, 0. Those are my x and y intercepts. I'm going to play connect the dots. And I get a line through like so. Now what we're looking for is the point of intersection. And I would like to point out that the graphing technique usually is only viable if your solution occurs at integer values of the coordinates. That means your ordered pair needs to be integers. So it looks to me like this ordered pair where they intersect is going to be at 3, 1. It does have to be x, y. And then what I highly recommend you do if you're solving by graphing, I highly recommend that you check that. So here's how you check to see if that really is the point of intersection. First, you plug it back into the first equation, 3 plus 1 equals 4, and that had better check out. And it also has to check out in the second equation, 3 minus 1 equals 2. So if you substitute your point of intersection into your two equations, and one of them fails to equal out, then you don't have the correct solution. Okay, for our next example, problem number 7 from the same section, 3.1. They again ask us to solve this system of linear equations by graphing. This problem is different because our equations are written in function notation, which, believe it or not, that actually makes it a little bit easier for us to graph, because function notation, what that means, it means that you're actually in slope-intercept form. F of x, g of x, both of those mean y. So you've got y equals mx plus b. And so if you know the slope and the y-intercept, you can graph pretty easily. Okay, so let's cover that technique. So for f of x, our slope is 1 and our y-intercept is -1. So if you know the poem for graphing slope-intercept form, it says plot the b, rise and run, connect the dots, and then you're done. Plot the b, that's your y-intercept. Rise and run means that your slope needs to be a fraction, and then that's going to be rise over run. So from the value of b, we're going to rise 1 and run 1, and that gets me to a new dot. Plot the b, rise and run, connect the dots, and then you're done. Now, let's do that again. This time for g of x, our slope is -2, and our y-intercept is +5. So here we go. 1, 2, 3, 4, 5. We're going to plot the b, rise and run, -2 over 1, connect the dots, and then you're done. Now we are looking for the point of intersection, which appears to be about there, which appears to me to be over at 2 and up at 1. So I think that's the point of intersection. We're going to write that over here, 2, 1. And I am going to check that again. All right, here we go. So to check, in the first function, f of x means y. So we're going to say 1 equals x is 2 minus 1. 1 equals 2 minus 1. That is correct. That does check out. For the second function, g of x also means y. So that's going to be 1 equals -2 times 2 plus 5. So 1 equals, that's going to be -4 plus 5. -4 plus 5 is 1. And so that checks out. And so again, just to make it clear, if you're going to solve by graphing, you have to be pretty good at keeping your scale accurate and graphing neatly in order to get this point correct. And if your point of intersection is not integer coordinates, graphing is not a very good technique for finding the point of intersection. In fact, it's a terrible technique if your lines don't intersect at integer coordinates. Okay, one more example from this section, 3.1, number 17. This is like a special case. Notice that our first equation has an x and no y variable, and our second equation has a y and no x variable. So these are special lines. I'd like you to know that x and no y is vertical, and y and no x is horizontal. So if we're going to graph these, if we're going to solve by graphing, this should be super easy. For the first equation, we're just going to go to 4 on the x-axis, bam, and draw a vertical line. And I just noticed I didn't put my L there. And for y equals -5, we're going to go to -5 on the y-axis, bam, and we're going to draw a horizontal line. Remember that we are looking for the point of intersection. Super easy if your lines are vertical and horizontal. That's going to be at the ordered pair for -5, which I don't know if you noticed, but that corresponds to x and y, 4 and -5. And that'll always be true if you have a vertical and a horizontal line. Now, just for fun, let's play the what if game. 17, let's call this version B. What if they would have both been x and no y? Well, that means that they would both be vertical lines, but they would be vertical at different x values. So in that case, since they're both vertical, they would run parallel, and parallel lines never intersect. And so in that case, you would have to write no solution. That would be a no solution problem. Also, if they both had y and no x, they would both be horizontal, which means they would be parallel and also have no solution. Now, for our next example, we're going to jump over to section 3.2, looking at problem number 3. In our list of techniques for solving, now we've looked at graphing. The next we're going to look at is substitution. So I might mention that if you're going to use substitution as a technique for solving a system of equations, you do have to have a variable by itself. So here, notice the x is by itself, and that means that x equals this stuff in the red box. Now, if x equals that, what that means, it means I can go to the other equation and replace x with it. That's what substitution means. It means you're going to go to the second equation and substitute for the variable that you have isolated. So drawing this arrow like so, we're going to have 2y plus x gets replaced with 3y minus 3, because that's what x equals 9. And now I have a single equation in terms of y, so I can solve for y. So let's combine like terms. 2y and 3y, that's going to give me 5y. Minus 3 needs to move over, making that positive. 9 and 3 is 12. And then if I divide both sides by 5, I'm going to get my y coordinate. And so the y coordinate of this solution is 12/5, which is not an integer value, and that means that solving this problem by graphing would be a nightmare and near impossible to get that correct. Okay, but we're not done. Remember, we're looking for the point of intersection. So the next step, once you know y, is to come back up here, and we're going to find x. So x equals 3 times y, which is 12/5, minus 3. And then I need to work this out to get what x is. So in my opinion, the easiest way to calculate this value is with the calculator. 3 times 12/5 minus 3 works out to be 21/5. So that gives us our x coordinate, 21/5. And now we can write the solution of the system, okay? The point of intersection, remember that has to be x comma y. So that's going to be 21/5 comma 12/5. Now, if you want to, you can plug that back in and check it like we did on the first and second examples, but I'm not going to take the time to do that. I've already demonstrated how to plug back in and check. So if you want to, on your own, you can take the coordinates. Remember, for it to be the solution, it has to work in both equations. So you will have to plug it back into both and make sure it works out. And before I move on, since I like giving as much instruction as I can, I am going to give you, I guess, an alternate way to check that's a lot easier than plugging the answer back in. As long as you're not taking a test, if you're just doing your homework and trying to check your solutions, DESMOS is a great tool. So what we're going to do is we're going to plug in both equations and we're going to check the point of intersection. Okay, so notice I have both of the equations typed into DESMOS. I have them turned off currently because I wanted to show you, as I turn these on, you're going to see the lines come up and they do intersect. Now, to check this point of intersection in DESMOS, all you have to do is click on the point, and it's going to give you a decimal. It's not going to give us the fraction values, but it's going to be easy to convert these to decimals and check those if you have a calculator. So again, like we have the CLASSWIZ here, gives us the 21/5. If I want a decimal, I can click the SD, and notice there's the 4.2. That was the X coordinate, and the Y coordinate was 12/5, which was 2.4. So again, with your calculator here, you can check these solutions. Even though DESMOS doesn't give you the fractions, you can convert these fractions to decimals with a calculator. All right, so for our next example, I'm going to do number 3 from section 3.2. And if you're going, wait a second, I thought you just did that. Yeah, I did, but guess what? We're going to do it again, okay? Like Britney Spears. Oops, I did it again. But this time we're going to demonstrate the addition method. Previously, we solved number 3 using the substitution method. Now we're going to solve it again using the addition method and show you that there's more than one way to solve this problem, and we should get the same answer. Now, in order to solve with the addition method, both of your equations need to be in standard form. So for the first equation, I need to switch the x and y so that it's in standard form. X plus 2y equals 9. In the second equation, I'm going to need to bring the 3y over, and that's going to give me x minus 3y equals negative 3. Now, when you're doing the addition method, what you want to do is you want to add the two equations together and get one of the variables to cancel. So notice the y's, if I add them, they are definitely not going to cancel, but the x's are close. If one of these x's were negative, then adding would get them to cancel. And so that's an easy fix to get one of the x's to be negative. I'm simply going to take the bottom equation and I'm just going to distribute -1 throughout. Now what that'll do is it'll simply go through and change all the signs. And then I can add and the x's will cancel. So did you catch that? If your x's are identical, just make one of them negative to get them to cancel. But that means you have to change every sign in that equation. So adding x minus x cancels. 2 plus 3 is 5y. 9 plus 3 is 12. And then if I divide both sides by 5, that's going to give me y is 12/5, which if I scroll back up, notice that that does match the answer we got in the previous technique. Okay, so then how does this work using the addition method? If I know x, how do I go and get the y then? Well, what you can do is take this value and plug it back in to either one of the original equations. It doesn't matter which one you plug into, you'll get the same value. Remember, since I'm looking for x, if one of the equations does have x by itself, then that's probably the equation that you want to plug into. So that's going to say x equals 3 times 12/5 minus 3. And remember, the easiest way to work this out is with a calculator. Now, for those of you that don't have a calculator, I'm going to go through this time and show you how to do it manually. Multiplying 3 times 12/5, 3 times 12 is 36/5 minus. Now, this 3 is understood to be over 1, and so we're going to need to get a common denominator here. Multiplying top and bottom by 5 gives us -15/5. And then we can subtract. 36 minus 15 is 21. You do not subtract the denominators, you keep them the same. And so that gives us an x coordinate of 21/5, which notice that that does correspond to our previous work through. So there's number 3, done again, demonstrating the addition method. And now, just for fun, let's go ahead and demonstrate how the CLASSWIZ can solve this for us. Now, the reason I didn't bring this up previously is because in order to solve with the Casio CLASSWIZ, your equations also need to be in standard form. So I wanted to wait till I got to standard form before I brought this up. Here's how you do it. We're going to go to the menu. We're going to scroll down to equation/function. Because we are solving equations, we're going to hit equals, and this time we are solving simultaneous equations. System of equations is simultaneous equations, number 1. And it wants us to pick the number of unknowns. That's the number of variables, which we have 2, x and y. And then if you look real close, you're going to see that it lists both equations in standard form. All I need to do is input the coefficients. So going back to the blue equation, the coefficients were 1, 2, and 9. 1 equals 2 equals 9 equals. For the second equation, originally it was 1, -3, -3. So we're going to input what it was originally. 1, -3, -3. And then if I hit equals again, it's going to give me the x coordinate of the point of intersection. And if I hit equals again, it's going to give me the y coordinate of the point of intersection. So the Casio CLASSWIZ will solve a system of linear equations in 2 variables, but your equations need to be in standard form. Next example, number 15 from section 3.2. We're going to do one more example of solving by substitution. Here, notice that the second equation has x by itself. So that means we're going to take the 3y plus 2 and plug it in for x in the first equation. And that's going to give me 2 times 3y plus 2, right? Replacing the x with what it's equal to, minus 6y equals 4, and then I simply solve for y. Doing the distributive property to get rid of the parentheses, we're going to get 6y plus 4 minus 6y equals 4. And all of a sudden I have a bad feeling about this. Watch this. 6y minus 6y. Oops, the y's canceled. So what does that leave me with? 4 equals 4. My variable disappeared. How can I solve for the variable if it disappears? Well, if all of your letters disappear like this, what it means that you're either going to have no solution or infinite solutions. If the remaining equation is true, which 4 equals 4 is true, that means that you're going to have infinite solutions. Whoa, okay, so if you're wondering how can you have infinite solutions, remember what we're actually doing here is we're finding the point of intersection of 2 lines. So if I go to DESMOS, I've already got these equations typed in, and I want to show you what happens when I turn them on. There's the first equation graphed. Now watch this. Bam, there's the second equation graphed. Do you see that? They're laying on top of each other. So how many points do they intersect at? Well, all of them. That's how you can have an infinite solution set, because they basically touch at every point. Now, there is a special word for that you need to know. If you have infinite solutions, means the equations are dependent. And the other key word there that you need to know is consistent. Okay, so again, what these words mean, dependent means infinite solutions. Consistent means that they touch at least one point. So you probably need to know both of those terms there. Our next example is, again, we're going to do number 15, but if you notice this is different, it's because this is from section 3.3, and we're going to look at solving this system using the addition method. Remember, that's also known as the elimination method. And for the addition method, what you want to do is you want to add the equations together and get one of the letters to cancel. Now, the 2's are pretty close to canceling if one of them was negative. And notice the y's are also pretty close to canceling if one of those 4's was positive. So what I'm going to do is I'm going to take one of those equations and I'm going to distribute a -1. Let's take the top equation. If I distribute -1, that simply changes all the signs, and then I can add them up. So let's add them up. -2x plus 2x cancels. No x, and you don't have to write 0x, it's just nothing. But look at this, 4y minus 4y also cancels. So what's left on this side? Nothing, just 0. On the other side, -5 plus 6 is 1. Now, on the previous example, I said if all of your letters cancel, you're either going to have no solution or infinite solutions. If your remaining statement is true, that is infinite solutions. Our remaining statement is false. And I bet you can guess what that means. Yeah, that means that we're going to have no solution this time. Now, again, if you're wondering how can two equations have no solution, remember what we're finding is the point of intersection. So is it possible that two lines never intersect? Well, we're going to go to DESMOS and show you. Here I've got the two equations typed in. As I turn them on, what do you notice? They are parallel. So as I scroll out, notice that they're going to be parallel forever, and that means that they're going to cross when? Never. And so that's how you have no solution. Now, on the previous example, I did cover two special terms that you needed to know. This example also has two terms, okay? So if your equations have no solution, we say that they are inconsistent. And we also say that they are independent. Okay, so here's what these terms mean. Inconsistent means no solution. Dependent means the same line. Independent means different lines. Inconsistent means no solution. Consistent means at least one solution. So try to make sure that you know what each one of those terms mean. So based on your particular set of equations, you'll know the terms that you need to use to define them. For my last example in this lesson, we're going to look at problem number 11 from section 3.3, and I'm going to try to be as comprehensive as I can. If you're given the option of choosing whichever method you want, here's what you need to look for. If all of the variables have coefficients, substitution is not the best technique. I highly recommend using the addition method if all of your variables have numbers in front of them. So in this case, we are going to use the addition method, which means that both of these equations need to be written in standard form. So the first equation is good, but the second equation is not in the right order. So we're going to switch the x and y. That's going to give us -3x plus 7y equals -5. And now that we have both of our equations in standard form, we're going to try to determine which variable would be the easiest to get it to cancel. Using the addition method, remember you want to add and get one of the letters to cancel. So looking at the x's, it's not going to be very easy to multiply 3 by something and make 5. But if you look at the y's, it's really not easy to multiply 7 by something and make 9. So it looks like that we can pick either x or y. They're both going to be equally difficult to get to cancel, or equally easy if you know my technique. So what I'm going to do is I'm going to pick on the x's and get them to cancel. They already have opposite signs. So the technique is, what you're going to do is take the coefficients of the x's and switch them. So the -3 goes here. And by the way, you do need to take the absolute value of these numbers if they're already opposite. So the -3 goes up here as +3. The 5 comes down here. And then what we're going to do is we're going to distribute the opposite coefficients to each equation. One more time, did you catch that technique? If the x's and y's are not easy to get them to be the same and cancel, you just pick one of the variables. It doesn't matter. I'm picking the x's. You switch their coefficients, making sure that they're both positive as long as the coefficients were opposite to begin with. And then you're just going to use the distributive property. Distribute the 3 and then distribute the 5. And that's going to give me new equations of 15x minus 27y equals 21, and negative 15x plus 35y equals negative 25. Okay, so look where we're at. Now if I'm doing the addition method, look at this right here. Bam, do you see that's going to get the x's to cancel? So let's go ahead and finish adding. Negative 27 plus 35, well, that's the same as 35 minus 27, and that's going to be 8y, and 21 minus 25 is going to be -4. And then I can simply divide both sides by 8 and solve for y. And if I reduce to lowest terms, that's going to give me y is -1/2. And we're half done. Now we need to take that value and plug back into one of the original equations. It doesn't matter which one you pick. You need to plug into one of the original equations and solve for x. I'm going to pick the top equation. Okay, so here we go. That's going to give us 5x minus 9 times -1/2 equals 7. Negative times a negative makes a positive. That's going to be 5x plus 9/2 equals 7. Moving the 9/2 over makes it minus 9/2. That's going to give us 5x equals, okay, so what is 7 minus 9/2? Well, you can either get a common denominator or you can use a calculator. And I highly recommend the calculator. So 7 minus 9/2, 9 over 2 is 9/2. Oh, improper fraction. Do we want it as a fraction? Yeah, let's keep it as a fraction. 5/2. And then if I divide both sides by 5, showing it like this, what I can do if I've got my calculator handy, I've already got the 5/2, I can just hit divided by 5, and that will give me the answer as a reduced fraction. So x is going to equal 1/2. Now that I know x and y, I can write my point of intersection. As an ordered pair, that's going to be 1/2, comma, -1/2. And if you're wondering, does it really matter what order those go in? Oh, yeah, because it's got to be x, comma, y. So that does make a difference. And as a special treat, we're going to go through how the Casio ClassWiz can solve this for you one more time. I've already done it once in this lesson. We're going to do it one more time just to reiterate the steps. So if you're at the home screen, and you want to solve a system of linear equations, remember the first step is they need to be in standard form. Then we're going to go to the menu, scroll down to the equation/function app, and hit equals. Then select number 1 because we're doing simultaneous equations with how many unknowns? 2. We only have 2 variables. And then you're going to input the coefficients. So for the first equation, we have 5, -9, and 7. And for the second equation, we have -3, 7, and -5. And once you input all of those values, if you hit equals again, OMG, look at that. X equals a half. And if I hit equals again, look at that. Y is -half. That is freaking sweet. I love this calculator. And then if you're done with that, the way you get back to the home screen is you just hit the menu and number 1 takes you back to where you can calculate. And that's going to do it for this lesson. So if you have any questions or comments about anything that I've covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.